Very good afternoon to all. I am Dr. Venkatachalam from the Chemistry Department of MIT. I thank the Jilla Panchayat authorities and Professor Magdodi for giving me this opportunity. Today we are going to discuss the topic that is P block elements. So when we look into the P block elements, they are the elements where the last electron enters into the P orbitals. So they will have the general configuration ns2. So the outermost s orbital is completely filled, and Nd 1 to 5, which starts with the 13th group member, and then 14th, 15th, 16th, 17th, 18th. They will come under the P block elements because the last electron enters into the P orbital of the atom. Out of that, today we are going to see only the group 15, 16, 17, and 18 members of the group, where 15th group is nitrogen family, and 16th group is oxygen family, 17th group is halogen family, and 18th group is the noble gases. So 15th group, they are coming under the 15th group because if you look into the electron configuration of that, they have 5 valence electrons there. And ns2np3, so 2 electrons in the s energy level, and 3 electrons in the p level. So there also you can see that there is ns2np3, so the p orbital is half filled configuration here. So because of this half filled configuration, because of this P3 configuration, it is extra stable. We know that the orbitals with the half-filled electronic configuration and the completely filled configuration are extra stable, and therefore this accounts for the extra stability of the nitrogen family. Then comes the oxygen family. In the oxygen family, 16th group ns2np4 is the general electronic configuration of those elements which are present with this oxygen family. Is also called as they have a specific name that is called as the chalcogens. And the next one is they are called as chalcogens because they are the mineral forming or ore forming compounds from which the metals are extracted. Out of this, in this member, you have oxygen, sulfur mainly, where most of the ores are in the form of oxides or sulfides, and from them the metal is extracted, and therefore they are termed as chalcogens also. And here you have the halogen family, halogen, salt forming compounds. So these elements starting from fluorine, bromine, iodine, etc., they have the ability to react with the metals to form salts, and therefore halo means actually salt forming. Gens means forming. So they are salt forming compounds. They are called as halogens. So 17th group members are halogens, and then these are the 18th group members. They have the electron configuration ns, general electron configuration ns2s6, and 8 electrons are there in the valence shell. Exception is the helium, which is having only 2 electrons there. 1s2 is the electronic configuration. That is an exception. But other than helium in the noble gas family, we have ns2np6. They are noble because of their lesser reactivity. They're less reactive because of, or they don't react in general. They don't react because of their completely filled electronic configuration, or their octet is complete, and because of that, they are less reactive. So if you're looking into the group oxidation state in general, 15th group will show the oxidation number as 5, and 16th group plus 6. This is general, but we have their variation, and 8 for the 18th group number. And if you look into the other oxidation states, it can vary from -3 to +3 for the nitrogen family, and it can go from -2 to +4 for the oxygen family, and for the halogen family, you can see -1 to +5. Various numbers, and for even for noble gases +2 to noble gases +2 to 6 is possible. So here, if you look into the first members of these in rock elements, particularly 15th, 16th, 17th, 18th, we always find that these first members are exceptional. They have some special behavior. They do not agree with the common property, or they do not show all the common property whatever the other members show, and that can be mainly attributed to the smaller size and the absence of the d orbital, vacant d orbital, because they mainly belong to the second period. This nitrogen, oxygen, fluorine, helium, etc. So in the second period, only two orbitals are, two shells are there, two main energy levels are there. So when we have only two main energy levels, n is equal to 2. So when n is equal to 2, n I mean here the principal quantum number which takes value 1, 2, 3, etc. This n is equal to 1 represents K shell, n is equal to 2 represents L shell, n is equal to 3 represents M shell, and so on. So when we say that they are in the second period, the main energy level of the last electron is 2, n value is 2. So when n is equal to 2, the subshell d is not possible, because to have n is equal to have a d orbital, L value should be 2. L is 2 only when n is equal to 3. And therefore, we cannot have the d orbital in the case of the first member of these groups. And because of that, they do not show some of the properties or multiple variable oxidation states or forming several compounds, etc. They show anomalous behavior. The other one is because of the smaller size, higher electronegativity, etc. is another reason for the anomalous behavior. So if we are going through, so here I have written, they have the general electron configuration NS2 and P1 to 6. So then before going into the question, if I'm specifically looking into some of the general properties or some of the general information, but if at all I want to say something, the first one is regarding the 15th group element nitrogen family. You have their NaNO3. If I ask you what is the name of this, you may say it is sodium nitrate, which is one of the source of nitrogen. Nitrogen is abundantly present in the atmosphere. Other than that, even on the Earth's crust, it is present in the form of NaNO3, which is called as chili saltpeter. So this is the chemical composition of chili saltpeter, NaNO3. At the same time, you have KNO3, potassium nitrate, that is called as Indian saltpeter. This is Indian saltpeter. This is chili saltpeter. And then you have the general properties, or the variation in the properties, such as if at all you are looking into the metallic, non-metallic characteristics. We know that nitrogen and phosphorus are nonmetals, and arsenic and antimony are metalloids. The 15th group, I don't have the members of the 15th group there. I'm sorry for that. And followed by we have bismuth, which is a metal. So this is how the property metallic character varies. So the first two are non-metals, next two are metalloids. They have the ability to show the metallic as well as non-metallic character, and the last one is the bismuth, which is a metal. And the oxidation states, which I have already mentioned there. Next is the compounds of nitrogen. Out of that, very specifically, I want to mention about the ammonia, NH3, which is very important compound commercially also, because ammonia is used for the production of several industrially important compounds, including the fertilizer, urea. So in such being that the case, ammonia is an important industrial process. Ammonia, NH3, is produced by the Haber's process. We all know that, and you know what is that Haber's process is, and also you know what is the condition to enhance the product of the reversible reaction, that is ammonia, probably in the chemical equilibrium chapter you have discussed about that, if not in the CET. And another important thing that I want to mention here is the brown ring test, which is done for the nitrate salt brown ring test. The salt is mixed, the salt solution is mixed with an equal quantity of freshly prepared more salt solution or ferrous sulfate solution. It has to be freshly prepared. You have to remember that. And then we have to add concentrated sulfuric acid along the sides of the test tube. At the junction of the two layers, we are getting a brown ring. So normally the question comes, what is that brown ring is? So that part we have to remember the chemical composition of that, the brown ring. And then if we are moving on to the second member of the nitrogen family, phosphorus, we have their various allotropic forms of phosphorus, white phosphorus, red phosphorus, and black phosphorus. Phosphorus, white, red, and black. These are the three allotropes. Out of that, black phosphorus is the most stable one. And then we have the various oxidation states I have mentioned here, that is -2 to +4. And then anomalous behavior of oxygen can be explained based on its smaller size and the non-availability of the d orbitals, vacant d orbitals. And also we have to remember that this oxygen, even though the electron configuration is ns2np4, so it's a pair of electrons. In spite of that, it is paramagnetic in nature. Using the concept of the molecular bonding, you know how you can explain the paramagnetic behavior of oxygen, even though it has even number of electrons. Please look into that, and once again brush up your knowledge regarding the molecular orbital theory and the paramagnetic behavior of the oxygen, even though it has the even number of electrons there. And the next one is some of the oxides, the compounds oxygen combines with the other metals, other elements to form oxides. So whenever the oxides are formed, we can have acidic oxides, we can have basic oxides, we can have amphoteric oxides. Amphoteric, which shows acidic behavior as well as basic behavior. So in the case of the oxides which are acidic, normally the oxides of non-metals are acidic in nature, whereas the oxides of the metals are basic in nature, and some amphoteric oxides are also there. Say for example, we have the oxides such as manganese or vanadium, etc. So this manganese, vanadium, etc. Their oxides are acidic in nature, even though they are oxides of metals. We have to remember that. Metal oxides, they are acidic because of the higher oxidation state of these. And then we have some of the oxides which are amphoteric in nature. They will show the acidic behavior as well as the alkaline behavior. The oxide of aluminium, that is Al2O3, is one example for that. It is amphoteric in nature. Next comes there with respect to the neutral oxides. I forgot to mention that some neutral oxides are there. That neutral oxides are carbon monoxide, nitric oxide, nitrous oxide, etc. CO. Carbon monoxide, N2O, NO. These are neutral oxides. And moving on to the phosphorus, the next member there of moving on to the next member, there is sulfur. Sulfur also exists in various allotropic form. Out of that, bromic sulfur and monoclinic sulfur are the two allotropes of the sulfur. And there comes further, mainly sulfuric acid, H2SO4, one of the important, industrially important, commercially important compound, sulfuric acid, H2SO4. We all know that how important even the study of the process in which the sulfuric acid is prepared, and also you must know this oleum. What is that oleum? Oleum is the product which is formed that is later in the manufacture of sulfuric acid, that is later diluted to get the sulfuric acid of the required concentration there. H2SO7 is the chemical composition of H2SO7 is the chemical composition of oleum. And in the sulfuric acid, which in the manufacture of sulfuric acid, what are the steps involved? First is the formation of sulfur dioxide, followed by sulfur trioxide. It's a reversible reaction, you have to remember that. And then later the sulfuric acid formation, which is absorbed by the sulfur trioxide is absorbed by sulfuric acid from oleum, and this oleum is further diluted to get the sulfuric acid of required quantity. And the next one is the properties of sulfuric acid. A very important aspect of sulfuric acid property is it's a strong dehydrating agent. Other than the acidic character, it has the ability, and it is hygroscopic in nature. It has the ability to even absorb the elements of water. Therefore, C12 H22O11. C12 H22O11 is the chemical composition of chemical formula of sugar, sucrose. So it has a carbohydrate. It has H22O11. So 11 molecules of water as such, if you look into that. So therefore, when there are the elements of water in the sugar molecule. So when sulfuric acid comes in contact with the sugar, or when sulfuric acid is added to sugar, it removes these elements and the sugar gets charred. That is because of the dehydrating property of the sulfuric acid. So very often this question is asked. And the next one is the halogens. So coming on to the halogens, they're salt producers, I already mentioned. That is fluorine, bromine, iodine. Out of that, fluorine and chlorine are gases. Bromine is a liquid, and iodine is a solid. So that's what the variation of the physical properties. Once again, fluorine being the most electronegative and the smallest atom, it will have some special properties there, and also because of the smaller size there, and the electrons are very closer to the nucleus when they form the compounds, because of the inter-electronic repulsion. Some of the special properties of fluorine or the compounds of the fluorine can be explained based on that. And next one is also here we have to know that the halogen family is the most electronegative compounds, and they have the ability to form ionic compound with most of the metals particularly, and the ionic compounds with the non-metals because of the higher electronegativity. And then the next thing that we have to remember is about the bleaching powder there, because bleaching powder is a commercially important compound containing chlorine, and in that the bleaching action of SO2 and bleaching powder. This is the one which is responsible for the bleaching action, the bleaching powder, even though that is not specifically the chemical formula of the bleaching powder. So here, the bleaching action is because of the liberation of the chlorine, and that chlorine oxidizes the colored matter of the organic vegetable material, whereas here it is because of the reduction, and here it is because of oxidation. So the bleaching action of bleaching powder is because of oxidation. The bleaching action of the sulfur dioxide is because of reduction, and therefore normally this is temporary, and the bleaching action of the bleaching powder, when we do the oxidation by the release of chlorine, is permanent. So that's the important thing that we have to remember this. And then some interhalogen compounds also we have to remember. The compounds which are formed by the various members of the halogen family, fluorine and the lower members, because of the availability of the d orbitals, they can take part in the formation of the compounds. And similarly, the next one is noble gas. As such, they are noble because of the NS2NP6 configuration. But later, Bartlett found that we can form the compounds of noble gases also because of the comparable electronegativity of one of the noble gas. If you remember, that noble gas is Nate Bartlett, I was looking for the name. He formed the first noble gas compound actually, and further so many noble compounds are formed. And the next one, we will move on to the question. I think with the a brief introduction to the topic, we are moving on to the question, that is, which of the following is not tetrahedral? I did not mention anything about the shape or structure of the molecules. I thought we can do that as and when the question comes. And the first question is, which of the following is not tetrahedral shape? So normally the shape of the molecule is decided by the number of electrons paired around the central atom, and also the hybridization. So depending upon the hybridization, sp normally linear, sp3 is trigonal planar, sp2 is trigonal planar, sp3 is tetrahedral, sp3d is trigonal bipyramidal. Like that it goes. And but there once again, based on what type of electron pairs are there around the central atom. So here the central atom is the nitrogen, here it is sulfur, it is silicon, and here it is sulfur once again. So based on this nature of the electrons that is present around central atom, whether they are bond pairs or lone pairs, and also based on the Vesper theory, we can explain the stability of the molecule depending upon the bond angle, to which extent they are staying away. So based on that, their shape changes. So therefore, we know that water, the central atom oxygen, has 4 pairs of electrons, 2 lone pairs and 2 bond pairs. Whereas methane, CH4, that also has 4 pairs of electrons. In both the cases, the hybridization is sp3. Therefore, the expected geometry is tetrahedral, but it is not so. In the case of methane, yes, it is tetrahedral, and the bond angle is 109.5 almost. Whereas in the case of water, even though there are 4 pairs of electrons around the central oxygen atom, 2 are lone pairs and 2 are bond pairs. So the lone pair repulsion is highest. And in order to minimize this lone pair repulsion, the 2 so these will move apart, and therefore these will come closer, and therefore this has a bend shape or V shape. That's what we have studied. So accordingly, based on the number of electron pairs, bond pair or lone pair, we can decide the shape of the molecule. And here the right answer is SF4, because SF4 has sulfur, it is, and it has lone pair of electron on the sulfur atom. So oxygen, we know this belongs to the oxygen family, and 4 bonds it makes with the sulfur, and therefore It is not tetrahedral in the shape. Whereas the NH4 plus, which is ammonium salt or ammonium ion or silicon tetrachloride carbon family, and SO42 minus. All these are the sp3 hybridization and therefore tetrahedral geometry. Whereas here, because the hybridization lone pair of electron is one pair and 4 bond pairs, total 5 pairs are there in this case, and the hybridization is therefore sp3d, and the geometry is trigonal bipyramidal. Trigonal bipyramidal, I hope you know. Trigonal bipyramidal. 2 here and 2 on top of the. And next question is a radioactive element which can decay to give 2 noble gases. So radioactive element which will decay to give reactive 2 noble gases. And if you remember that that's a special case actually, thorium is the answer for that, and the radioactive decay of thorium will give the noble gas radon and xenon. So that is just a memorization there, you have to remember that. And the next one is a black compound of manganese, black compound of manganese, reacts with the halogen to give a greenish yellow gas. So one is what could be the black compound of manganese, one thing that you have to remember. You have to ask yourself, and the other thing is, what is that greenish yellow gas? That's the next thing that you have to think of or ask yourself. When an excess of this gas reacts with the NH3, so that greenish yellow gas reacts with the NH3, an unstable trihalide is formed. In this process, the oxidation state of nitrogen changes from. So what could have happened? What could have been, or what is the final product? That's what we have to look into. So manganese compound reacts with the halogen acid, some halogen acid, to give a greenish yellow gas. With that gas, when ammonia reacts, an unstable trihalide is formed, and the process in this process of the formation of this unstable trihalide, what is the change in the oxidation state? That's the question. And here, that black oxide, if you look into the reaction there, it is MnO2. And from MnO2, when MnO2 reacts with the halogen acid, it gives a yellowish, greenish yellow gas. Greenish yellow gas of halogen is acid is chlorine gas. And so HCl is produced here, NCl3. So here is the greenish yellow chlorine gas liberation, and the liberated chlorine Cl2 reacts with the NH3 to form NCl3. So in the entire process, the oxidation state changes from -3 to +3 there. And we look into the final product. So nitrogen here, chlorine is -1 into 3, therefore -3, and therefore to compensate that, this should be +3 nitrogen is. So that's how the variation of the oxidation state takes place. And the next one is pure nitrogen is prepared in the laboratory by heating the mixture of question is pure nitrogen is prepared by the reaction of dash and dash on heating in the laboratory. This is a numeric question. It is the reaction between ammonium chloride and so sodium nitrite, NaNO2, sodium nitrate. Please remember that it is not nitrate. So usually, you will get confused with this and this, but it is NaNO2, not NaNO3. And the next one is the geometry of XeOF2, xenon oxyfluoride. What is the geometry of the molecule? So the geometry of the molecule, as I mentioned once again, is decided by the number of pairs of electrons around the central oxygen atom. And here, if you look into the molecule, the shape is T-shape, and the reason for that is oxygen has 2 lone pairs of electrons, and then it is bonded with 2 fluorine atom and 1 xenon, and therefore there are with the fluorine 2 bond pairs and with the xenon 1 bond pair, so total 3 bond pairs. So, and 2 lone pairs, total 5 bonds. And therefore, the geometry of the molecule, you can see it is a T-shaped. So lone pair will come here, and the other 3 bond pairs will make the T-shape there. Therefore, the geometry of the molecule is T-shaped. And which of the following acids form 3 series of salts? 3 series of salts can be formed by the acid, which can liberate one by one hydrogen at a time, 3 times. So the basicity of the acid should be 3. It should be able to release 3 protons. So in such cases, it can form 3 series of salts. But here, unfortunately, if you look into the formula of the molecule, whatever is given here, all have H3, H3, H3. So very difficult. So which hydrogen is able to go as proton? That is a question. To know that, it is important to know the structure of the bonding. Whichever hydrogen is attached to the oxygen, that can be released as H plus. If it is directly attached to the central atom, so here central atom is boron, here it is phosphorus, here also it is phosphorus, here it is phosphorus. So if hydrogen is directly attached to the central atom, it cannot go as a proton. Therefore, I hope CH3COOH, acetic acid. It's a mono basic acid, even though there are 4 protons. Why acetic acid is a mono basic acid, even though there are 4 protons? Because only this hydrogen which is bonded to the oxygen can be released as a proton. Whereas these hydrogens which are bonded through a perfect covalent bond, nonpolar covalent bond to the hydrogen, they cannot be released as a proton. And therefore, it's basically so. Similarly, based on that concept, here also, whatever hydrogen is attached to the oxygen, whichever hydrogen is attached to the oxygen can be released as a proton, and therefore that will decide the type of salt that is formed. And if you if you are familiar with this, this is nothing but the phosphoric acid, and that has basicity 3, and therefore it will form 3 series of salts. And if you want to get the structure of that, here it is. So the 3 OH hydrogens are bonded to the oxygen there, and the one oxygen has no hydrogen, which is having a double bond there, and therefore it forms a series of salts such as NaH2PO4, NaHPO4, and Na3PO4. So this is how the salts are formed. And the next question is, xenon difluoride has xenon difluoride, XeF2. What is the shape of that? So that's what the next question is. I'm seeing some hand is raised today. Anyhow, let me move on. I don't know for what reason the hand raised symbol I am seeing. Anyhow, xenon difluoride, if you look into the molecule, it's a linear molecule, and the explanation goes like this. The hybridization of a molecule can be calculated based on, we have a formula to calculate hybridization. That is 0.5 into V plus M minus C plus A. So what is that? V is the number of valence electrons that is present on the central atom, and valence electrons, outermost electrons, and M is the number of coordinate, the number of pairs of electron it gets through the bonding, and C is the cations that is present, and A is the anions that is present. So here, if you calculate the total number of electrons, it comes as 10 there, 8 plus 2, and then comes 2 monovalent fluorine atoms are there, 2 monovalent fluorine atoms are there, so 2 electrons from there, and here it is 8 electrons on the central xenon, 8 valence electrons of xenon, plus 2 monovalent fluorine atoms. So total it is 10. And cation and anions are not there, and the divided by 2. So it is 5. So the coordination number or the hybridization is 5. And for that hybridization, trigonal bipyramidal should be the structure, and shape of the molecule is linear because of the presence of the lone pairs there. Here, 3 lone pairs you can see, and 2 bond pairs are there, and therefore this makes the shape of the molecule, even though the geometry is trigonal bipyramidal. And the next one is the oxidation state of central atom in the anion compound NaH2PO2. NaH2PO2. So it's a very simple one. Sodium is +1 and hydrogen is +1 plus 2 into +1 plus x, we don't know how much is that, plus 2 into -2. So if this has to be equated to 0, if you calculate that, you get the oxidation state of central phosphorus as +1. So this is how the calculation goes. And the next question is, a brown ring is formed at the in the ring test of nitrate ion, and it is due to the formation of brown ring is formed in the ring test for the nitrate, and it is due to the formation of, it's a common question which is asked actually most of the time, and the composition of that is and that takes place in a series of reactions actually. So when the freshly prepared ferrous sulfate solution is mixed with the nitrate salt, and freshly prepared ferrous sulfate solution or more salt solution is mixed with the nitrate salt, and sulfuric acid is slowly added into that. First of all, there is a formation of NO, nitric oxide, and that nitric oxide will combine with the iron complex, which is formed there because of the addition of the ferrous sulfate to form nitroso ferrous sulfate. It is nitroso ferrous sulfate, the name of that compound is. So sulfate is not written here, ferrous 2 plus, and the sulfate anion will be there. It will be in the ionized form, and the chemical composition of the species which is responsible for the brown ring is nitroso ferrous sulfate. And the next question is, the bleaching powder is treated with the CO2. So when the bleaching powder is treated with the CO2, what happens? Question whether it absorbs the gas, or whether CaO is formed, or whether CaCl2 is formed, or whether calcium carbonate and chlorine gas is formed. So this is a knowledge about the subject or the chemical reaction understanding that we need to have. So calcium carbonate will be formed when bleaching powder is reacting with the carbon dioxide, and the reaction is CaOCl2. This is species which reacts there with the carbon dioxide to form CaCO3 plus Cl2. And the next one is the reagent which is used to distinguish between H2O2 and O3, hydrogen peroxide and ozone. Whether it is BBS, whether it is bleaching powder, whether it is starch and iodine, or whether it is KMnO4. So here the answer is KMnO4. KMnO4 because when you look into the oxidizing ability, H2O2 can decolorize the KMnO4 according to this equation, whereas ozone can activate only the soluble or insoluble manganese into permanganate ion, but it will not oxidize. So it is not so strong enough to oxidize the KMnO4, whereas H2O2 can oxidize the KMnO4. Therefore, the color changes. And the next one is, which of the following elements can be involved in p-pi-d-pi bonding? Here, by looking into this p pi d pi, you don't have to worry much. If you look at the options, it's very easy to get the answer from this. Carbon, nitrogen, boron, phosphorus. If you look at this carbon, 14th group member, that comes in the second period. Nitrogen, 15th group member, comes in the second period. Boron, 13th group, whereas phosphorus, nitrogen family, sorry, nitrogen family, that is the third period. So it has the d orbital there, and therefore, because of the availability of the vacant d orbitals, that is the answer which has the ability to form p pi d pi bonding here, and it can be involved. Whereas these are in the third period, sorry, second period. So when they are in the second period, they don't have the vacant d orbitals available there, and therefore they cannot form the bonding involving the d orbital. When sugar is treated with the concentrated sulfuric acid, the sugar is charged. I already explained this charring of the sugar. It is getting dehydrated. That is the answer. If you look into the reaction, we know that I already mentioned it. C12H22O11 gives 12 carbon plus 11 H2O. So that's the special dehydrating property of sulfuric acid. It is hygroscopic in nature, dehydrating in nature. It has the ability even to remove the elements of water, that is hydrogen and oxygen. Of the following hydrides, which is the strongest reducing agent? Strongest reducing agent. So here comes the variation of the properties down the group, the variation of the hydrides down the group. Phosphorus, acetine, bismuth, and nitrogen. So nitrogen, phosphorus, acetine, bismuth. So all these come in the same group. So down the group, if you are looking into, the stability decreases. If the stability decreases, it's the ability to lose hydrogen, to give the hydrogen for the reduction of the others is faster, and therefore that will act as the strongest reducing agent, and therefore bismuth is the right answer. Reducing character of hydrides increases from top to bottom in the nitrogen family there, because the stability decreases. The lesser stable, more unstable, greater is the ability to reduce. Next is N2O3 is whether it is a basic oxide and anhydride of HNO2, or it's an acidic oxide, or anhydride of HNO3, neutral oxide, and anhydride of HNO3, acidic oxide, and anhydride of H3. Anhydride is the substance which is formed, or a molecule which is formed by the removal of water molecule from the acid. So we have to look into, if we add water to this, if we add one H2 into this formula, what we get. And if you look into this reaction, the reaction is N2O3 plus H2 gives 2 molecules of nitrous acid, HNO2, and therefore HNO2 nitrous acid. So, but here there are 2 nitrous acids, so therefore we are looking into whether it's a basic acid, basic oxide, or acidic oxide. Nitrous acid being HNO2 being acid, which is produced by the oxide N2O3. So any oxide on reaction with the water, if it produces acid, if the solution is acidic, then that oxide is called as acidic oxide, and therefore N2O3 is acidic in nature, and therefore this is the right answer. And the next one is, which of the following oxides react with both HCl and NaOH? To react with the HCl, it should be a base. To react with the base, it should be an acidic one. So the oxide is basic as well as acidic. If it is basic, it reacts with the HCl, or reaction with the HCl illustrates the basic character. Reaction with the NaOH illustrates, explains the acidic character. That means it should be an amphoteric substance. So if we look into these oxides, which one would be amphoteric? That's what we have to look into. That's what we have to think of. Calcium oxide, alkaline earth metal, calcium, second group, highly alkaline nature. CO2, oxide of carbon, it's acidic in nature. We know that it produces carbonic acid. N2O5. Most of the oxides of the non-metals which are acidic in nature, particularly nitrogen on the top there, it should be an acidic one. Whereas if you look into the zinc, that is amphoteric in nature. Whereas if at all we want to see the reaction of the zinc with the HCl, sorry, zinc oxide with HCl, it produces zinc chloride. Whereas the zinc oxide reacts with the NaOH to give sodium zincate. So therefore, zinc oxide being amphoteric, it reacts with the acid as well as the base, sodium hydroxide. And the next one is maximum covalency of nitrogen is covalency, ability to form bond. In general, we know that nitrogen can triple bond it has, whereas there are some compounds of nitrogen where nitrogen has the ability to bond with four other atoms. Say, for example, in the case of ammonium salts or quaternary ammonium salts, etc., nitrogen can make bonds with the four other atoms or groups. So therefore, in the case of ammonium salts or in the case of quaternary ammonium compounds, we can have the covalency of nitrogen as 4. So 4 is the answer. Next one is, which of the following reaction depicts the oxidizing behavior of sulfuric acid? To depict the oxidizing behavior of sulfuric acid, what should happen? That's what we have to look into. So oxidizing ability, we have to see from where it removes the hydrogen. That is one possibility that we can look into, or else we can think of changing the oxidation state. So here oxidizing behavior of sulfuric acid. So sulfuric acid should oxidize, the oxidation number of this one should change. So calcium is +2 here. Here also it is +2, no change, so it is not. And here it is PCl5, so it is +5. And here also 3 chlorine -3 -2 oxygen, and therefore here also it is not changed. It remains the same. NaCl plus, so here it is +1, and here also it is +1, so it is no change. Whereas in this case, hydrogen iodide, this is -1 iodine, and here it is 0. So -1 to 0, the oxidation number increased, and therefore it depicts the oxidizing behavior, or it shows, illustrates the oxidizing behavior of sulfuric acid. Therefore, that is the right answer there. So the reaction goes like this: hydrogen iodide with the sulfuric acid gives iodine plus SO2 plus H2O. So this is the reaction. And the next one is the solubility of iodine in water may be increased by the addition of solubility of iodine in water. So whether it is Na2S2O3, or whether it is carbon disulfide, or whether it is Ki, or whether it is CaCl3. If you have done the titration of iodine, iodometry, or iodimetry, when the iodine is liberated, we add potassium iodide to that, so that the liberated iodine is not escaping, and it can be titrated directly or immediately without much loss of iodine against sodium thiosulfate hyposolution. And therefore, we have to remember that the addition of Ki increases the solubility of iodine. Why it increases the solubility of iodine is the Ki will react with the iodine to form Ki3 minus. Ki3 I3 minus. Sorry, it's not. Ki3 or I3 minus ion. So this formation of this enhances or increases the solubility of the iodine, and this is the one which I wrote there. So Ki reacts with iodine to form I3 minus triiodide ion, and the triiodide ion is more soluble in water. And the next question is, pure chlorine is obtained. What is the method of obtaining the pure chlorine? And the pure chlorine is obtained either by heating BtCl4, or by treating the bleaching powder with the HCl, or by heating with the MnO2 and HCl. One of the method of preparation of chlorine it is, if you remember, or whether it is by heating a mixture of NaCl and MnO2 in the presence of concentrated sulfuric acid. And by knowing the method of preparation of chlorine, we know that it is by heating MnO2 and HCl. And the next question, okay, the reaction goes like this: MnO2 plus 4HCl giving MnCl2 plus H2O plus Cl2 gas. So this is the another method of preparation of chlorine gas. And the next one is the catalyst used in the Deacon's process for the manufacture of chlorine is Deacon's process. I hope you remember there is a manufacturing method of the chlorine gas, and the catalyst used there is the Kipler's chloride. And if you look into the reaction there, Deacon's process is the oxidation of the HCl, in the presence of Kipler's chloride, where the chlorine gas is liberated. And the next one is, which of the following halogen is a corrosive liquid? Fluorine, chlorine, bromine, iodine. Fluorine and chlorine, the first two members of the halogen family, they are gases, we know that. And the bromine is a liquid, this is a solid. And this is corrosive in nature, and the question is that it's a liquid, and therefore bromine is the answer. And the next question is, which of the hydrogen halide has the least bond dissociation energy? Bond dissociation energy. Bond dissociation energy is dealing with the ability to dissociate one mole of the bond. In fact, it is dealing with the strength of the bond strength. For which one the bond strength is less is the question. So whether it is HF, HCl, HBr, or HI. Stronger is the bond, closer is the bond, and bond energy or bond dissociation energy is more. And therefore, hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, if you look into that, we know that hydrogen iodide is having the weaker bond in comparison to HF or HCl or HBr because of the larger size of the iodine. And whenever the size is larger, the bond pair of electron is not attracted so strongly by the nucleus, and therefore the dissociation is easy, and therefore it has the least bond dissociation energy. And the next question is, identify the correct statement. Bleaching action of SO2 is temporary. Bleaching action of chlorine is permanent. Only option A is correct. Both A and B are correct. I think now you are in a position to answer this question, because in the beginning, knowingly or unknowingly, I mentioned about the bleaching action of sulfur dioxide as well as chlorine. And therefore, bleaching action of SO2 is because of reduction. So it is temporary, because any coloring matter or vegetable got bleached is undergoing reduction there. But that bleached substance, when exposed to the moisture, the air that is present or the oxygen that is present, they will further oxidize it back to give the original color. And therefore, it is temporary. Whereas in the case of bleaching action of chlorine, the bleaching action is because of the oxidation. And the oxidation bleaching is always permanent. And therefore, the correct answer is the fourth one, both A and B. And the next one is, which of these is not a poisonous gas of chlorine? Not a poisonous gas of chlorine. So in this question, to give the answer specifically, very clearly with the confidence, you must know the chemical composition of all. But if you don't know also, you can manage this by trial and error. Phosphine is the one which you can remember easily. Phosphine, pH 3. So if you know that that is the answer which does not contain the chlorine, then rest everything should contain chlorine. And otherwise, you have to remember very specifically the chemical compositions of the tear gas, phosgene, and mustard gas. So this tear gas contains chlorine. Phosphine is pH 3. Phosgene is also contains chlorine, and the mustard gas is having chlorine there. And the next one is the shape of the interhalogen compound ClF, whether it is linear, a T shape, or square pyramidal, or pentagonal bipyramidal. So if you are looking into the answer of this, the ClF is a linear molecule, And next question is the composition of aqua regia. Always this aqua regia is a confusing one because we know that it is made up of nitric acid and nitric acid and hydrochloric acid. But the question is, depending upon whether you write HCl or HNO3, this ratio changes. We also know that it is in the ratio 3:1, but this which is 3, which is 1 is always confusing. And therefore, somehow you have to fix it. Maybe you fix it HCl and HNO3, HCl and HNO3 in the ratio 3:1. So somehow you have to fix it. Otherwise, by seeing the change in the position, you may get confused whether it is HCl3 or HNO3. And therefore, please remember that it is the HCl and HNO3 in the ratio 3:1. HCl3, HNO3, 1. So here, everywhere it is written HNO3. Please remember that. Therefore, 1:3. So somehow please fix that. Otherwise, whenever you see this question, when you are answering that independently at your own level, you will get confused. HCl versus HCl and HNO3 in the ratio 3:1. Therefore, HNO3 and HCl in the ratio 1:3. And next is, which of the oxy acid of chlorine has maximum oxidation state of chlorine? Once again, here you must know the formula here: chlorous acid, hypochlorous acid, chloric acid, perchloric acid. Without remembering the formula, you may not be able to get the answer for this. After writing the formula, you should be able to calculate the oxidation state here. HClO2, this is +1, and oxygen is so it is 1 +1 plus X plus -2. Therefore, what is the oxidation state of chlorine? We can calculate here. And similarly, here it is +1 plus X plus -2. And here it is +1 plus X plus 3 into -2. And here it is +1 plus X plus 4 into -2. So which all should be equal to 0. And therefore find out the X. So if you do that, you will get the answer as perchloric acid, because the oxidation state will be maximum there for the chlorine atom and the minimum will be there for this one. Okay. Solving for X will give you the answer. The next question is, the most abundant noble gas in the atmosphere is, once again, very direct question based on the memory. You have to answer this question, and the answer is argon. The most abundant noble gas is argon. And the next one is, which of the following is anhydride of perchloric acid? Once again, here the name of the various acids of containing chlorine and their chemical composition you must know, and then the anhydrides of that you can get by the removal of water, which molecule is formed. So here, therefore, if you look into this, the answer is Cl2O7, and HClO4 is the formula of perchloric acid. Perchloric acid on heating loses one water molecule, 2 molecules of this, and it gives Cl2O7, and therefore the anhydride of perchloric acid is Cl2O7. And the next is, what is the hybridization of xenon in xenon tetrafluoride? Once again, you have to look into the number of unpaired electrons there, and if you look into the number of unpaired electrons and also the number of bond pairs, you will get that it is sp3d2, because sp3 will give 4 orbitals and d2 will give 2 more, so total it becomes 6 orbitals there. So on the HCl4 you have 6 electrons, 6 pairs of electrons there. To accommodate that, you need the hybridization sp3d2, and one of the last question. The number of unpaired electrons in a noble gas atom. This is a quite interesting question. Very simple. At the same time, many people can do mistake in this. The number of unpaired electrons in the noble gas atom is. Noble gas have 8 electrons in the valence shell, and therefore, when we have 8 electrons in the valence shell, they are all paired, and therefore the number of unpaired electrons in the case of noble gases is 0. And last question is, bleaching powder is prepared from the reaction of slaked lime and chlorine, picked lime with the chlorine, burnt lime and chlorine, calcium and chlorine. I think this is the same word is there in your, even in your NCERT book, this burnt lime and chlorine. So this ends the questions which I prepared for the day. So if you have any questions, you can put in the chat box. Otherwise, thank you so much. And I wish you all the best. Once again, I thank the Jilla Panchayat authorities and the organizers for giving me the opportunity on behalf of my institution MIT and on my personal behalf. I wish you all the best. Thank you.